Good evening. I'll share my screen 1 minute. Welcome to the problem solving session for week 5 for the course Introduction to Wireless and Cellular Communications. I'm your tutorial instructor Sachin from the EC department in the Indian Institute of Science. As usual, today I'll be solving a few problems that are very similar to the assignments that you have, so that it is actually helpful for you to solve your assignments. Question 1 says a constellation diagram is a scatter plot of the complex modulated symbols in the xy plane. A binary phase shift, phase shift key modulation transmits a symbol +1 or -1 in one symbol period. Shown below is the constellation of 100 BPSK symbols. So this is the stream of symbols that was sent through the transmitter. Either +1 or -1 was sent, and all of them have the same in-phase component. All the +1s have the same in-phase component, -1s are exactly opposite, and they have zero quadrature phase component. Now, assuming that Doppler is the only channel impairment, and you assume that there is not even noise, so even the noise is zero, how will the constellation look for the received values? That is, what does the Doppler have? What effect does the Doppler have on the scatter plot? The answer is, since we are assuming that there is no path loss and there is no noise, or there's only Doppler effect. Since there's no path loss and there is no noise, that means all your received values have the same power, because the Doppler effect won't change the power of the signal. It is only a change in the apparent frequency and phase. And hence, since we are taking the power to be the magnitude of the power, the amplitude is 1, so the power is 1. So the worst that can happen due to Doppler is that uh, some of the power went from your in phase component to your quadrature phase component. So Doppler can cause a change in phase, but the overall power has to be the same. So what that means is that this is the zero level, then the constellation has to lie on a unit circle. That is it should be a point that is at a distance of 1 from the center. So think about that. You can look at the options and see in which option the points all lie on a unit circle. And that will be your answer. Another remark is the Doppler shift introduces phase shift on the transmitted symbols. Here, this is 1, this is -1. Hence, the received values will lie on the unit circle. You can go back to your lecture and see how the Doppler affects only frequency and phase and not the amplitude. The second question says three channel impulse responses are plotted below. Which of the channel impulse responses correspond to the channel width, the smallest bandwidth? There is one channel response C. So this is in log scale. Sorry, it's not in log scale. This is a time axis. The actual values are not important for us. It's the amplitude. So one of the impulse responses is like this. Another impulse response is it's following the same kind of trend, but it's varying faster than. The black one is C, the blue is A, and the red one is B. So the thing we have to be aware of here is that the time resolution is inversely proportional to the channel bandwidth. Less resolution means smoother impulse response. So the one which has the smoothest impulse response will have the smallest resolution in time, and that will have the largest bandwidth. So out of the three curves, you have to look at which one of them has the highest time resolution. That will give you the answer. This is a question that is similar to something we saw last time. Consider a scenario where the receiver is between the transmitter and a reflecting wall, and moving towards the reflecting wall. As the receiver is closer to the wall, which of the signals corresponds to the resultant wave received? So this curve A is just a smooth curve. Curve B is uh, I'll draw this diagram is not very accurate. You should just check in your assignments. Anyway, this is a sinusoid that's very, very fast. So the slow varying curve is curve A, fast varying one is curve B, curve C is one which is kind of like the product of the two curves. Anyway, you can check the assignment for the exact diagram. This is just a rough sketch I've drawn. This is curve C. So, which one of these is the signal that the receiver sees when it is moving towards the wall and it is close to the wall? This For this you have to refer to lecture 19 notes. There's no mathematics involved here. It's just a theoretical question. So if I tell you the answer, since it's a question from the current assignment, I can't just tell you the answer, but at least I can tell you where you can find the answer. Okay, let's see. Question 4. At least I can tell you for this. Um, This is case 5. Okay, there are many cases which were taught. Many so case 1 is a fixed receiver antenna, and only the uh, mobile is moving, mobile station is moving. Case 2 was receiver antenna and receiver antenna was moving. Case 3 there was a reflecting wall. Case 3 we saw a problem in last week's problem solving session. In case 4 there's a reflecting wall and receiver antenna is moving. So case 5 is the case in this question where there's a reflecting wall and you have a moving receiver antenna, or it's actually case 5 was a moving reflective antenna, but here our mobile station is moving, but they are kind of equivalent cases and you are close to the wall. So in this case, we had something like 2 alpha over d sine of 2 pi fc into t minus d over c into sine of 2 pi fc d over ct plus r0 minus d over c. So last time when we were solving the problem, the two components were getting added up. And when we are close to the wall, uh, you can actually there are two uh, cosine components that you can simplify it into a product of two sine components. You do some trigonometry, then you'll get a received signal of the form a sine multiplied with a sine. So that's why you had one of them is a slow moving sine, one of them is a fast moving sine wave, and your actual received signal is a product of those. If I tell you any more than that, then I will have to tell you the answer directly. Okay, we'll go to question 4. A relay fading channel model R is Zs plus N, where Z is distributed. What is the probability that the received signal power is at least 8 dB below the mean power? So received signal power PR is mod z square gamma, gamma is E of mod s square by E of mod n square is the mean received signal power. What you want to find is the probability that PR is 8 dB lesser than that. It's the probability that so from dB I'll write it in normal power terms. P received is not in dB. That's why I have to write my mean digit signal power minus 8 dB in terms of power. And that is, and since mod z square will have exponential distribution with mean 1. So the probability that mod z square is less than 0.158 is the integral from 0 to 0.158 e power minus x dx, and you do the integral, you'll get the answer. Consider a hello. Ah, ah, 1 minute, I'll see. That is 1 by 10 power 8. There is uh, this gamma is there on both sides, no? Let me check. I haven't done the calculation myself, but let me do it. See, so the gamma will get cancelled from both sides. So this is nothing but P of mod z square less than 1 by 10 power 0.8. And that is 0.158. 1 by 10 power 0.8 is 0.158. Okay. Now this integral, you can do it. and you find the value of that integral, that will be the answer. Question 5. Consider a system that uses coherent QPSK modulation and detection scheme with 10 microsecond symbol period for communication. The channel has a coherence time of 4 millisecond if 100 symbols are being used for transmitting training sequences or channel estimation. Find the data rate without considering the training overhead. So we have coherence interval is coherence time is 4 milliseconds. So total number of symbols transmitted in one coherence interval is Tc. This is Tc by Ts. Ts is symbol duration. It's 4 millisecond by 10 microsecond. Here you have 10 microsecond. So you're sending 400 symbols in the coherence interval, but as you can see, 100 symbols are being used for transmitting training sequences. But 100 symbols are used for training sequences. So Data that is being sent is only 300 symbols. So data rate without considering the 100 symbols overhead is if you're sending 300 symbols in 4 milliseconds. Oh, I shouldn't have said that. Anyway, 300 symbols of data in 4 milliseconds. Well, you find the data rate. Next question. Consider a flat fading system. R is equal to Z times S plus N as explained in the lectures. And Z has the distribution Cn of 0, 1. If a deep fade occurs when the SNR falls below 0 dB, that is mod Z whole square times gamma is less than or equal to 1. Calculate calculate the approximate probability of a deep fade at high gamma. Probability of deep fade is the probability of that's where gamma being less than or equal to 1, which is the probability that that's where less than or equal to 1 over gamma. Now mod Z square follows an exponential distribution. So the probability that mod z square is less than or equal to 1 over gamma is the integral from 0 to 1 over gamma of e power minus x dx. You carry out the integration and you will get the answer in terms of gamma. And um, one thing here is that you'll get the answer in terms as a function of gamma, but there will be terms of the form e power 1 over gamma or something like that. Then you have to use the fact that uh, gamma is high, right? You have to use, if gamma is high, 1 over gamma is very low, and for low 1 over gamma you can use an approximation to e power 1 over gamma. So you use an approximation, use a linear approximation, ignore the higher order terms, then you'll get the right answer. You'll get one of the options. So this part where you're finding P of z square less than or equal to 1 over gamma is similar to the last question, except that here instead of giving you the actual value uh, of 1 over gamma, you have the answer in terms of gamma. So, and you actually have to use the fact that gamma is large to do an approximation. Oh, well, the approximation is f of x approximately f of 0 plus f prime of 0 times x when x is approximately equal to 0. You can use that. Next is a very basic question. If PE denotes the probability of bit error, then what is the probability that two independent bits are recovered without any error? Well, we know that for two events A and B, if A and B are independent, then probability of A intersection B is probability of A times probability of B. You can use that and you can call your event A as the probability that first bit is in, there's no error in the first bit. A can be the event, no error in bit 1. And B, you can take it as the event, no error in bit 2. Then you can use the independence to find the probability that both the bits are recovered without any error. For QPSK, assuming EB over N naught is equal to 8 dB, evaluate bit error rate in AWGN channel, additive white Gaussian noise channel, using the exact expression. So EB over N naught has been given in dB. And to find the exact BAR, we need to know EB over N naught in normal ratio terms. So 10 log EB over N naught is 8. EB over N naught is 10 power 8 over 10 in a normal scale. So you find that. Then for QPSK in the AWGN channel, the bit error rate is simply given by Q of root of 2 EB by N naught. So you can substitute the value of EB by N naught and you can use the online Q function calculators to find the value of BAR. Ah, final exam I have not written, so I don't know, but I think they will give if they want you to find it out. Yeah. Uh, Actually, I am not sure because I have not written the exam myself. No, is it an offline exam or online exam? Online. No, I don't think. See, I don't think they will expect you to calculate Q values yourself. You can't really do it. So if they ask you something like this, they will maybe they will give the value directly, or they will give you the link. They might just give you Q value for certain. They might give you a table of Q values. Certainly, they won't expect you to know the Q value of these Q value directly, and they won't expect you to. Yeah, they will give the Q value if it is needed, or they won't ask this type of question, or they might give the options in terms of Q value. Then in the previous question, find a CR, symbol error rate. So this is quadrature phase shift keying. For QPSK, one symbol has 2 bits. What is the symbol error rate? This probability that the symbol is in error is probability that first or second bit is in error. Is the probability that first bit in error plus probability that second bit in error minus P of first or second bit, first and second bit are both in error, which will just be P of first bit in error into P of second bit in error. Because errors are, we are assuming that errors are independent. Errors in each bit is independent. So, like I told in the one of the previous questions, for independent events, the probability that both events happen is the product of the probability that each of the events happens. Now, for one bit, we know the probability of bit error. We know the bit error rate. So this is nothing but 2 times Q of minus Q of squared. So that will give you the symbol error rate for QPSK. So you know Q of square root of 2 EB by naught from the previous question. You just have to plug in the values and you'll get the answer. Question 10. What is the rise factor K for a channel with no line of sight component? Rise factor is nothing but power in line of sight component divided by power in non-line of sight component. So power, regardless of what power in non-line of sight component is, Here in this question, there is no line of sight component. So power in line of sight component is 0. What does that mean for rise factor? The next question asks, how does the rise factor K change with a decrease in the power of the line of sight component? And from the formula, we can see that rise factor is directly proportional to power in LOS component. So if you fix your for a fixed power in non-linear sight component, rise factor and power in LOS component will vary the same way. Which of the following gives rise to statistics similar to that of a Rayleigh PDF? And options, we have Ricean distribution with k equals 0, Ricean distribution with k equals 1, Nakagami M distribution with m equals 1. D is A and C both. Rayleigh fading is the same as Ricean fading without a line of sight component. So what is the value of k when there is no line of sight component? You have to find that out. Then you'll know if Rayleigh fading matches Ricean distribution with k equals 0 or k equals 1. In Nakagami distribution with m is equal to 1, we'll have to go to the lecture and check if that matches relay fading or not. It will either match or it won't match, so I can't tell you the answer directly. You'll have to go and check in the lecture videos. Question 13 asks what is the most appropriate multipath model for cellular transmission, where a dominant LOS plus many weak reflections are present. Options are again Rayleigh, Rician, Nakagami, or both B and C. So we already seen that Rayleigh fading is the same as Rician fading without a line of sight component. So if there is no line of sight component, there's no point in modeling. So here there's a dominant line of sight component, so we can't really model that using Rayleigh fading. So it's not Rayleigh. So Bayesian is a distribution in which there is a strong line of sight component. You can in Bayesian fading there is a line of sight component, so you might be able to do it. You'll go back and check in your lecture videos. Nakagami also you can model if you have a line of sight component. That also includes one component, which is a line of sight component. Now, are these good models when the line of sight component is very dominant and the other components are very weak? That you go and check in the lecture videos. So, um, are there any restrictions on the line of sight component for Rician and Nakagami, or is it okay if the line of sight component is the dominant component that you go and watch the lecture videos? I've already told you it's not really. I'll skip the next two questions because they're directly based on the graph. So outage probability 5%, they have given you a dashed line which marks the required outage probability. And then they have uh, given you the received power versus so they've given the curves for different value of KR. You can just You can directly tell from the graphs. You just have to find the point where the um, dashed line for the outage probability meets the curve. So since there are three different curves or three different values of k, they will meet the outage probability at different points. Then the answer will be the negative of the value you find on the x-axis. That you can just do it yourself. I'll skip 14 and 15. Next question is 16a. Mobile communication system uses a DBPSK, differential BPSK modulation, DBPSK modulation scheme. So what that means is that the transmitter sends zero at the, we are assuming that the transmitter sends zero at the beginning of the transmission. Oh, bit zero is transmitted with phase zero. So we're assuming zero is the uh, plus component, plus A, and bit 1 is transmitted with phase pi, so it's minus A. If the following binary data stream zero one one zero zero one has to be conveyed to the receiver, which of the following is the correct bit stream that is sent to the transmitter after the differential modulation. Assume that the zeroth bit is 0. So I will call given bit stream and denote it by ik for different values of k. And then I'll call the differentially modulated bit stream. I'll call it bk. So for differential modulation, your bk is bk minus 1 XOR ik. Now they have given that the zeroth bit given b0 is 0. So your b1 is b0 XOR I1. So I1, I2, I3, I4, I5, 0, 1, 1, 0, 0, and I6. You're transmitting 6 bits. B1 is B0 XOR I1, which is 0 XOR 0 is 0. B2 is B1 XOR I2. B1 was 0, so this is 0 XOR I2 is 1. So this is 1. B3 is B2 XOR I3. It's 1 XOR 1, which is 0. B4 is B3 XOR I4, which is 0 XOR 0, which is 0. B, B5 is B4 XOR I5. Finally, B6 is B5 XOR I6. Well, I actually shouldn't have told you the answer. But anyway, BK is BK minus 1 XOR IK with B0 set to 0 and I1 to I6 given is the given bit stream. 17 is a theoretical question. You can find the answer in the lecture videos. 18, calculate the BER of coherent BFSK in Rayleigh fading if the average SNR is 8 dB. Gamma is 8 dB, which is 10 power 8 over 10, which is 6.31. No, BER of coherent BFSK for Rayleigh fading is given by half of 1 minus square root of gamma divided by 2 plus gamma. Okay, question 19. An M by N interleaver takes Mn bits as input, inserts them column-wise into an M by N matrix, and the output bits are produced by reading the elements of this matrix row-wise. Consider a 8 by 10 interleaver at the transmitter. Which of the following blocks can de-interleave? I'll just tell you the answer. If you have an interleaver of size I by j, then you can de-interleave by using an interleaver of size j by I. So you're just doing the reverse process. Okay, those are the questions in this week's assignment. Most of the questions I have given you the method to solve them. You just have to go back and actually do the calculations. Any questions? Uh, I by j inter. If you have an I cross j interleaver, then as a d interleaver for this I cross j interleaver, you can use a j by I interleaver. That will work as a d interleaver for the I cross j interleaver. See what an interleaver does is it puts the bits in columns and then reads them row wise. Then you put the D interleaver, you put the rows in columns and read them. The Put the bits in columns again and they read it row wise. That's all. So the J by I interleaver will do the exact reverse process of the I by J interleaver. You can check it this way. You m is equal to we can try one example. M is equal to 2, n is equal to 3. Let's say you have 1 0 1 0 1 1. So I don't have an example on hand. Let me see if I can cook up an example. Okay. Uh, Sorry, in this example, this is m is 3 and is 2. Right, you have this input bit stream that what you do for interleaving is you put it in a 3 by 2 matrix like this. So first bit goes here, then second bit goes here. So you first fill the first column, 101. Then you fill the second column like this, 0. This one goes here, this one goes here, right? Then what the interleaver will give you as the output is you read it row wise. So you'll get 1 0 0 1 1 1. This is what the interleaver will give you. So you see that 1 0 1 0 1 1 got scrambled in this way. So bits got mixed up. So to de-interleave this, you use a m is equal to 2, n is equal to 3 interleaver. So in a m is equal to 2, n is equal to 3 interleaver, there will be 2 rows and 3 columns. So you get 1 0 0 1 1 1. Now you put them in 2 rows and 3 columns. So in first column you will have 1 0. Then in second column you put 0 1. Then in the third column you put 1 1. So this is what A 2 by 3 interleaver will do, right? It will put your data bits, 2 bits in each column, and then it will read it row wise. So you're reading it as 101, 011. So you got back the original uh, stream of bits before interleaving. So that's why if you have a m by n interleaver and you use that interleaver to do your interleaving, then the interleaved bit stream you can give it to a n by m interleaver, and that will do the reverse process. You'll get back your original bit stream. So this is one example I came up with. I don't know exactly in which way the streams are put in the columns and rows, but this is one way you can do it. All right, that's it for today's session. I'll meet you next week. Good luck with your assignments.